So what if I told you that the key to building, like the ultimate bionic superlimb, isn't stronger titanium, and it's not a better battery?
Right, which is what everyone assumed.
Exactly. What if the secret to next-generation bioimplants is actually taking a perfectly good biological muscle, literally cutting its lifelines, and deliberately plugging the completely wrong nerve into it?
I mean, on paper, it sounds like a surgical mistake.
Yeah.
But it turns out that specific quote-unquote mistake fundamentally rewrites the biophysics of muscle tissue.
Yeah.
Like, we've spent decades trying to engineer these synthetic motors to match human biology.
And we've just been missing the point.
Totally missing the fact that our own biology is wildly programmable, if you just change the inputs.
And that right there is the mission for our deep dive today. We are exploring this genuinely wild 2026 paper out of MIT's K. Lisa Yang Center for Bionics.
Published in Nature Communications.
Right. And for everyone listening, what these researchers managed to do is take a native, easily exhausted muscle and hack it into this computer-controlled cyborg actuator. And it's 260% more fatigue resistant.
Which is a massive jump.
It's huge. And they did it by basically throwing out the entire rule book on how nerves are supposed to work.
And I think it's important to state up front that the implications of this research stretch way, way beyond just building a better robotic arm.
Oh, for sure.
We are looking at a framework that could allow us to mechanically actuate failing internal organs or even modulate human psychological states on demand.
Just by using our own re-engineered tissues. It's science fiction stuff. But okay, to understand the sheer magnitude of this MIT paper, we first have to look at the huge roadblock engineers have been hitting in biohybrid systems, right?
The actuator problem.
Yeah, because whenever you try to build a bionic limb or an implantable device, you need an actuator, like the motor that actually does the moving and the lifting.
And historically, we've relied heavily on synthetic ones, pneumatics, hydraulics, electromagnetic motors.
But the bottleneck with those synthetics is always scaling and power density, right?
Exactly. The moment you try to miniaturize a pneumatic or hydraulic system down to the centimeter or even millimeter scale, which you absolutely need for a medical implant, the efficiency just plummets.
They just generate too much heat.
Too much heat, and they require these super bulky external battery packs. And honestly, maybe the biggest issue is that they are inherently non-biocompatible.
Right, because the human immune system is exceptionally good at identifying foreign plastics and metals.
And just walling them off.
Yeah, so the obvious pivot for scientists is to look at the actuator that evolution already perfected, which is skeletal muscle.
Which is basically the perfect nanometer scale molecular machine.
Right, it runs on ion gradients and, our body's own ambient metabolic energy. It scales from the microscopic level all the way up to the macro level without losing efficiency.
And if it tears, it fixes itself.
Exactly. No titanium servo is going to just self-repair after a mechanical failure.
Right. And integrating that biological actuator with a computer is, at least conceptually, pretty straightforward. You just use a minimal synthetic component, like a little nerve electrode, to interface with the muscle.
So the computer sends an electrical signal through the electrode into the nerve, and boom, the muscle contracts.
Exactly. And that process is known as functional electrical stimulation, or FES.
Okay, FES, which sounds like a totally solved problem. But obviously you look around and amputees aren't walking down the street right now with perfectly integrated computer-controlled biological muscles.
No, they definitely aren't.
So when I was reading through the literature on FES, it seems the major failure point is just fatigue. The muscle tires out incredibly fast under computer control.
It does.
So why is a computer-stimulated muscle so much weaker than, say, a brain-stimulated muscle?
Well, it all comes down to the biophysics of motor nerve architecture. Specifically, this concept called axon diameter.
Okay, break that down for us.
Sure. So if you look at a native motor nerve, let's use the tibial nerve, which controls the calf muscle in the ward. The nerve fibers, or the axons inside it, are highly non-uniform.
Meaning they're all different sizes.
Exactly. You have a massive variance in the cross-sectional area of those fibers inside the nerve bundle.
So picture a bundle of different sized pipes, basically.
It's a perfect way to visualize it. Now, when your brain naturally controls that nerve, it follows a very specific recruitment order. It recruits the smallest fatigue-resistant muscle fibers first for sustained, low-effort tasks.
Like just standing or walking.
Right. And it only calls on the massive, fast-twitch fibers for explosive, high-effort movements.
But functional electrical stimulation, FES, it doesn't have that biological nuance, does it?
Not at all. When a computer fires an electrical current into that non-uniform bundle of motor axons, the physics of electricity dictate that the current will take the path of least resistance.
Right.
And the largest diameter axons offer the lowest electrical resistance.
Oh, I see. So the electricity flows through the biggest pipes first.
Exactly.
Yeah.
So FES forcibly recruits the largest motor units first.
And those large motor units are tied directly to the fast-twitch muscle fibers, right? The ones that tire out instantly.
You got it. So instead of a gradual, sustainable burn, the computer is essentially just flooring the gas pedal in first gear.
Wow.
It triggers all the explosive force immediately, entirely depleting the muscle's energy reserves in a matter of seconds.
Which is why the force drops off so fast.
Yeah, the consequence is this catastrophic drop-off.
Yeah.
Under continuous FES, a native muscle suffers an exponential weight of fatigue. It quite literally falls off a physiological cliff.
Making it totally impractical for a continuous biological motor. So just to do a quick recap for everyone listening, we need bioactuators because synthetic ones are bulky and get rejected. Biological muscles are great, but they tire out way too fast under computer control because our motor nerves have uneven sizes, right?
That is the perfect summary.
Okay, so if the non-uniform size of the motor nerve axons is the root problem causing this reverse recruitment, the logical fix is to find a uniform nerve.
Which brings us to the core of this MIT experiment.
Yeah.
They created something they call the Myoneural Actuator, or MNA.
MNA.
Okay, they took a rodent model, isolated a leg muscle called the lateral gastrocnemius, and completely severed its native motor nerve.
So they cut the tibial nerve, totally eliminating the muscle's natural connection to the brain and spinal cord.
Yes, but to preserve the tissue and make it controllable, they performed a surgical reinnervation. They spliced a completely different nerve into the muscle.
And this is the crazy part.
Yeah, they used the sural nerve.
Okay, wait, I have to push back on the biology here for a second. Because the sural nerve is a sensory nerve.
It is.
Its entire evolutionary purpose is to pick up tactile information from the skin and send it UP the spinal cord to the brain, right?
Exactly.
But motor nerves send commands down to the muscle. Are you telling me they literally reversed the traffic on the neural highway?
I know, it sounds insane.
Because biologically, a sensory nerve shouldn't even speak the same chemical language as a muscle fiber.
Your skepticism is completely justified, and it is precisely why this discovery is so paradigm-shifting. You're right. Sensory nerves inherently lack the native architecture to drive motor function.
So how did it work?
The histological analysis in this paper revealed an extraordinary degree of biological plasticity. The sensory nerve fibers didn't just physically grow into the muscle, they underwent a profound functional adaptation.
What kind of adaptation?
They actually established cholinergic synapses.
Wait, cholinergic synapses, meaning the sensory nerve fibers actively recognized that they were attached to a muscle now and somehow figured out how to synthesize and release acetylcholine.
Yes.
But that's the exact neurotransmitter required to trigger a muscle contraction. How is a sensory nerve doing that?
It underwent a localized phenotypic switch. The sensory axons successfully restored functional neuromuscular junctions across the entire muscle tissue.
That is staggering.
It really is. This regenerative phenomenon was thought to be nearly impossible in prevailing neurobiology. The tissue essentially reprogrammed itself based on its new physical environment.
It turned a passive sensory wire into an active motor interface.
Exactly. The tissues are just blindly seeking connection and function.
Okay, so the hack works. But let's bring this back to the fatigue problem. Why use the sensory nerve in the first place? Like, why the sural nerve?
Because unlike motor nerves, sensory nerves have a highly homogeneous, uniform axonal population.
Oh. Their cross-sectional area is all the same size.
Remarkably consistent, yes.
Okay, so when the computer applies the electrical stimulation to this new sensory nerve, there are no quote-unquote large pipes for the electricity to favor.
Exactly. The current is forced to distribute evenly across the entire nerve bundle.
Which means the muscle fibers are recruited evenly and impartially. No more flooring the gas pedal.
Right. And the data reflecting this is definitive. The researchers subjected the MNA to continuous FES and compared it to native motor innervated muscles.
And what were the numbers?
The native muscles fatigued exponentially, losing almost all their force in roughly 5 seconds.
5 seconds? That's nothing.
But the MNA demonstrated a 260% improvement. It sustained its force output for nearly 19 seconds.
And reading the data, It's not just that it lasted a few seconds longer, right?
Yeah.
The actual shape of the fatigue curve completely changed.
Yes, this is the physics shift.
Because the native muscle drops exponentially, just a straight cliff. But the hacked M&A muscle showed a logarithmic fatigue dynamic.
Exactly. It drops slightly initially, and then it levels out, maintaining this highly stable plateau of force.
You've fundamentally changed the math of how the tissue tires out. So just to recap this section, scientists cut the motor nerve, attached a uniform sensory nerve instead. The sensory nerve miraculously formed motor connections, and the muscle became a fatigue-resistant superactuator.
That's it. You have engineered a fatigue-resistant, closed-loop biological actuator. It provides the sustained, predictable force output that engineers need, but without any of the bulk or biocompatibility issues of synthetic motors.
Which is brilliant, until we consider the long-term reality of actually having this in a living body.
Right, the atrophy question.
Yeah, because if we sever a muscle from the central nervous system, it is totally isolated. The brain isn't sending it those ambient background signals that normally keep a muscle toned.
Yeah.
I mean, if an astronaut loses muscle mass just by floating in zero gravity for a few weeks, shouldn't an entirely isolated, disconnected muscle just wither away and die from disuse atrophy?
Denervation atrophy is a huge, critical hurdle in tissue engineering. Without efferent neural signaling from the CNS, skeletal muscle undergoes rapid apoptosis.
It just breaks down and dies.
Exactly, losing mass and contractility. The assumption going into biohybrid design is that you would need to constantly shock the muscle with maintenance FES just to keep the tissue alive.
But the researchers track these M&A cohorts over a massive time frame, right? Like 9, 12, and 15 weeks post-surgery.
They did.
And during that entire multi-month window, they applied absolutely zero external electrical stimulation?
None.
So what happened to the muscle mass?
It remained completely stable. Yes. The M&A maintained its mass and its maximum isometric force across all time points, with no significant degradation whatsoever.
How is it self-sustaining without the brain signals? That makes no sense.
Well, while the sensory nerve was disconnected from the brain's motor cortex, the physical presence of the reinnervated sensory axons provided enough localized neurotrophic support to prevent the muscle from breaking down.
So just the physical connection itself is enough?
Yeah, the sensory nerve acts like a localized life support system. It maintains the cellular health of the tissue, so it's primed and ready the exact moment the computer decides to activate it.
Okay, so we have a self-sustaining, fatigue-resistant motor. But the control mechanism still relies on FES, meaning we are still shooting electrical currents into a nerve inside a living animal.
Right, which brings up the safety concern.
A huge safety concern. Because sensory nerves are literally wired to transmit pain and sensation. If the computer is hitting this sensory nerve with electricity to move the muscle, isn't that signal also going to travel the other direction, straight up the spinal cord, and cause excruciating pain or sensory overload for the host?
Unintended neural afference is a major issue, yes.
Right.
If you are operating a bionic limb and the actuator's control signals bleed into the CNS, you compromise the entire system and cause immense discomfort.
So how did the MIT team get around that?
They anticipated it, and they integrated a reversible electrical nerve block.
And the parameters on this block are fascinating. They apply a high-frequency alternating current, specifically 20 kilohertz, at 8 volts peak-to-peak proximal to the brain, upstream from where they stimulate the muscle.
Exactly.
But how exactly does hitting a nerve with a high-frequency shock block a signal? That sounds backwards.
Think of it as localized active noise cancellation for the nervous system.
Okay, I like that.
The 20 kilohertz signal is so rapid that it forces the sodium ion channels in the nerve fibers into a state of continuous depolarization.
So they get locked open.
Essentially, yes, they become locked. The electrical gates simply cannot reset fast enough to allow any other signal to pass through that specific section of the nerve.
Oh, wow. So you've essentially created a temporary electronic firewall, like setting up a soundproof door in a hallway?
That's exactly it.
So on one side of the firewall, the computer is throwing a loud party, blasting the nerve with stimulation, driving the muscle to contract and do heavy lifting. And on the other side of the firewall, the brain registers absolute silence.
Absolute silence. And crucially, it is completely reversible.
Really?
Yes. The moment the computer turns off the 20 kilohertz signal, the sodium channels reset, and the nerve returns to its completely normal state.
That is so elegant.
The researchers proved they could achieve highly accurate, closed-loop force tracking of the MNA while simultaneously silencing all neural conduction to the brain.
Okay, quick recap for you listening. The M&A survives on its own without shrinking, and we can electronically mute the connection to the brain so computer control doesn't cause any pain.
Right.
So we've solved the actuator problem. We have built a perfectly isolated, self-sustaining biological motor that doesn't fatigue and won't cause pain.
But a motor is useless without a chassis, right?
Exactly. If we actually attach this to a human, say an amputee, how does this isolated biological motor interface with their remaining anatomy?
And this transitions us to the first major clinical application outlined in the paper, addressing the profound lack of proprioception in modern bionic limbs.
Okay, proprioception. For everyone listening, proprioception is your body's innate ability to sense its position in space without looking. Like if you close your eyes and bend your elbow, you know exactly where your hand is.
Because of the sensors in your arm?
Right. But amputees using robotic prosthetics don't have that. The brain is entirely blind to what the synthetic limb is doing unless the user is actively staring at it.
That's because the brain relies on mechanoreceptors embedded in our native muscles and tendons. When a biological muscle stretches, those receptors fire signals to the brain, which the brain intuitively maps as movement.
But a robotic limb has no biological mechanoreceptor.
Exactly, so the brain receives zero telemetry.
To solve this, the researchers developed what they called the proprioceptive mechanoneural interface, or PMI.
The BMI. Right.
They took their newly engineered M&A muscle and they surgically coupled it in series to a native residual muscle left over in the amputation site.
In the study, they used the medial gastrocnemius as the residual target.
So how does that work mechanically?
The M&A in this setup basically functions as a programmable biological tensioner. When the computer detects that the robotic limb is moving in the physical world, it sends a proportional signal to the M&A.
Okay.
The M&A contracts, and because it is physically sutured to the residual native muscle, it exerts physical strain. It literally tugs on the native tissue.
And the moment that residual native muscle gets physically stretched, its biological mechanoreceptors wake up. They feel the strain.
Precisely. And the research team measured this interaction meticulously. They used stenomicrometry.
Which is using sound waves to track the exact physical strain on the tissue, right?
Yes. And they paired that with electroneurography, or ENG, to actively monitor the neural signals traveling up the native nerve to the brain.
And the results of that pairing are just incredible. The M&A physically pulls on the residual muscle, and the residual muscle sends a perfectly natural biological signal to the brain saying, hey, I am stretching.
And because of how neuroplasticity works, the brain intuitively maps that stretching sensation directly onto the robotic limb.
The brain literally thinks the robot arm is part of its own body.
The stenomicrometry and ENG recordings confirmed a highly correlated dose-dependent relationship. As the M&A pulled harder, the neural afferents increased proportionally. So the brain perceives the mechanically induced strain not just as a vague pulling, but as the dynamic, real-time articulation of the bionic joint. You are providing genuine, high-fidelity biological proprioception for a synthetic machine.
So recap number 4 for you listening. We can use the M&A to tug on leftover native muscles, completely tricking the brain into physically feeling a robotic limb.
It's a huge leap for prosthetics.
The elegance of that solution is stunning, but the MIT team didn't stop at orthopedics, did they?
No, they took this self-sustaining cyborg motor and applied it to internal medicine.
They built a biohybrid organ.
Which makes sense when you abstract the concept of an organ. I mean, many of them are simply biological pumps relying on mechanical actuation.
Right. The diaphragm is just a pump for air, the bladder is a pump for fluid.
And the gastrointestinal tract is a sequential pump for digestion.
Okay, so how did they test this in the gut?
In the paper, they demonstrate this by physically wrapping the M&A around a section of a small intestine.
Oh, wow.
And they filled that intestine with a colored saline solution to simulate the presence of food.
Okay, so the cyborg muscle is just hugging the intestine.
Exactly. And under computer control, they initiated a localized actuation sequence. The M&A contracted, physically squeezing the intestine.
Like artificial digestion.
Yes. Using optical flow analysis, they verified that the M&A could perfectly mimic the organ's natural mechanical movements. It seamlessly reproduced the sequential peristalsis required to propel matter through the gut.
If we look at the clinical applications for this, it immediately targets severe gastrointestinal motility disorders, right?
Definitely.
Things like postoperative ileus, diabetic enteropathy, or severe Crohn's disease where the gut simply paralyzes itself.
Instead of relying on systemic drugs with massive, awful side effects, you could wrap a patient's own reprogrammed muscle around their intestine and have a computer artificially jumpstart their digestion.
It acts as an implantable biohybrid assist device. But the implications of mechanically actuating the gut go far deeper than simple digestion.
Oh, absolutely. Specifically when you consider the gut-brain axis.
Yeah, this is where the intersection of biomechanics and neurology gets a little surreal. Because the gut is incredibly dense with mechanosensors, isn't it?
It is. So when the M&A mechanically squeezes that intestinal wall, it isn't just pushing fluid around. It is physically activating a vast neural network embedded in the tissue itself.
And activating those enteric mechanosensors triggers profound physiological cascades. Like it induces the release of systemic hormones, most notably GLP-1.
GLP-1.
Which is the exact same hormone pathway currently dominating the medical field for weight loss and metabolic control.
Exactly. So modulating the gut-brain axis through direct mechanical actuation allows you to manipulate appetite and energy balance right at the source.
But it gets even crazier than that.
It does. Because more profoundly, the gut-brain axis regulates deep psychological states.
Right.
By artificially controlling the mechanical rhythm of the gut, you are actively influencing neurological feedback loops related to mood, anxiety, and just overall cognitive baseline.
Let that concept really sink in for a moment for everyone listening. By having a microcomputer contract a hacked biological muscle that happens to be wrapped around your intestine, you could theoretically write an algorithm to treat clinical depression or anxiety.
It's wild. You are translating code into mechanical force and mechanical force into neurochemistry.
So our final mini recap. The M&A can wrap around failing internal organs, pumping them artificially to restore digestion and even manipulate our psychological state.
It completely reframes our entire approach to autonomic control. The M&A proves that we don't necessarily need to engineer better synthetic machines to fix the human body.
Right, we just need to use what's there.
We simply need to understand the programmable nature of the biology we already possess.
Yeah.
If we can apply this localized control to the lungs, the bladder, the heart, or the gut, the M&A serves as a universal tissue-engineered motor for the future of regenerative medicine.
And because this relies entirely on autographed skeletal muscle, meaning the surgeon uses the patient's own tissue, you bypass the entire nightmare of immune rejection that plagues traditional synthetic implants and organ transplants.
Your body completely accepts the motor because the motor is you.
Wow. The design flexibility demonstrated in this paper is just unparalleled. We've successfully bypassed the fundamental biophysical limitations of functional electrical stimulation simply by observing that sensory nerves possess a more advantageous geometry than motor nerves.
And trusting that the tissue would just adapt to the connection.
It has been such a wild journey through this research. We started by looking at the glaring flaws of putting metal and batteries inside the human body. We identified that our own muscles are the ultimate nanomachines, held back only by the uneven wiring of our native motor nerves.
And by replacing that motor nerve with a uniform sensory nerve, the researchers completely shattered the fatigue barrier, yielding an actuator that performs 260% better.
And one that sustains itself indefinitely without brain input and can be electronically firewalled to prevent sensory overload.
We've seen how this biological motor can act as a tensioner to give amputees a true sense of touch and spatial awareness for their robotic limbs.
And we've seen how it can wrap around failing internal organs, acting as a programmable pacemaker that might one day literally alter our neurochemistry and our moods.
It forces us to reevaluate the boundaries of tissue engineering. We are no longer limited by the evolutionary function of a specific nerve or muscle.
We can isolate them, recombine them, and program them to execute entirely novel behaviors.
Exactly.
So for everyone listening, I want you to consider the sheer untapped potential residing in your own biology. We are entering an era where your tissues aren't just static parts. They are raw material waiting to be recoded.
Which leaves us with a profound question to explore as we close out today. Let's hear it. If we have definitively proven that we can isolate, rewire, and map a sensory nerve to act as a computer-controlled fatigue-resistant motor, what happens when we start upgrading the rest of the human architecture? If we can program our own gut to alter our mood on demand, where exactly is the line between a biological human and a programmable biomachine?
It really makes you wonder. We used to think the distinction between man and machine was obvious. You could just look at an X-ray and see exactly where the bone ended and the titanium began. It was clean, binary, visible. But looking at the Myoneural Actuator, that line isn't just getting blurry, it's disappearing altogether.